can you guys, hello. Wait, can you guys hear me in the back of the class? Yes?
Yes.
Yeah, if they weren't making so much noise with that wrapper.
Alright, so basically this is going to be your first taste of college chem, I think. And it's going to be on your mini exam, so hope you guys pay attention. I'll let you guys get like stuff if you want to take notes or something. You don't have to, but just
I'll take them all if I can.
So I didn't leave space on your chip because it's a third period special.
Will this be on other periods mini exams?
I don't think
Oh no. Oh,
This is part of day 85 for third period special.
but just in case.
Alright, so now that you guys are situated, so I'm going to be presenting on superacids and their chemical structures. So we'll just start with vocab. So I'm not going to go over everything on this
How does
slide,
it
but
do?
just the key ones I'll be like referring to throughout the presentation. So bronzite laurate, so that just refers to the bronzite laurate acid, right? By definition, that's just something that donates a proton to something else. So in this case, when I say proton, I mean an H plus ion, so keep that in mind. And a bronzite laurate base just accepts a proton, so that's pretty straightforward. Hydronium just refers to a proton plus water, so that's just H3O plus. And then protonation, I'll say that a lot throughout this presentation, that's just giving something an H plus. And then Ka is just the dissociation constant of an acid, so the higher the Ka, the stronger the acid is because the more it dissociates. And then pK is just a negative log of Ka, and this is just used to measure the strength of an acid, and the smaller it is, the stronger the acid is. We'll go into Lewis acids and bases a bit later, and then anhydrous just refers to anything that doesn't contain water.
I bet you they can figure out that last one. Anhydrous.
Alright, so what is a superacid? So it's just something that's stronger than anhydrous sulfuric acid, so it has a pKa of less than or equal to negative 2.8. And very strong acids will be measured with a special function known as the Hammett acidity function. And this is used for acids that make the pH scale irrelevant. And I'm not going to be going into this because this is beyond my knowledge. But here we just have structures of some superacids. Alright, so I'm displaying the same structures again, and I want you guys to just look at them and see if you guys notice anything interesting.
So I can
Alright,
rewatch
you
the
guys
rest.
notice anything interesting? Yeah?
May I record?
Yeah, you can record.
Well, I don't see this from
Oh, thank you, Mr. Cole.
Alright.
What? People!
Brayden?
They're like O. They're all connected to O.
Oh, yeah, most of them contain.
That's true.
That's true.
Yeah.
This goes back to Lewis structures
What
and
was it?
electron. That's the hint.
What?
They're all tetrahedral.
Yeah. Actually,
That's true too.
yeah. Alright, anyways.
How about something unusual?
They'll break the
Wait, no, you can't speak. You already heard this before.
They break the octet rule.
What?
Alright, yeah, so if you notice, like half of these break the octet rule. You see like chlorine has 7 bonds.
Oh, the 8 things.
S has 6 bonds.
breaks the
you notice they
octet
all
rule.
break the octet
Of
rule.
8.
So yeah, SNOS sucks. It's meant to be broken. Don't like generalize SNOS. And basically, chemical bonding is just more of a fight between all the atoms in a molecule to get the right amount of electrons. So some atoms will be left unhappy per se. So yeah, just remember that SNO does not apply for this presentation. Alright, so go more into superacid. Alright, so this is the formation of a traditional superacid. So you have a Lewis acid, a strong Lewis acid, and a strong bronzite laurate acid. And when you combine them together, you form a superacid. So you can see right here, you have
Wow.
HF plus antimony pentafluoride forms fluorantimonic acid. So, about Lewis acid. So basically, a Lewis acid is an electron acceptor, and a Lewis base is just an electron donator, right? As you can see right here, we have the Lewis base, O2 minus, plus Lewis acid, which is SO3. And basically when they combine, right, the Lewis base gives its electron to the Lewis acid, right, which is SO3. So as you can see right here, those two get donated over to this complex over here, and that basically forms an acid-base adduct. And so this is useful as it allows us, it shows that H plus is not really needed in order to be acidic, which is something you guys probably aren't familiar with. Okay, so now we have one category of superacids. So these are known as carburenes. and they're some of the strongest bronzite acids known. They have a really interesting structural formula, which is up on the board. And basically, they just consist of a boron-like shell almost, with a carbon on top. And then all of these over here, so you can see where it says Y and Z, those you can just like insert in random stuff. So you can see in that molecule over there, we have Cl's and then an H on top. So one important thing to note is that that H on top right there, the blue one over there, is not the acidic hydrogen, alright? So don't go saying that that one dissociates because it doesn't. Instead, the acidic hydrogen is actually a kind of shared between those two chlorine atoms on the bottom. Just keep that in mind. And these are useful because they're only being studied for drug delivery, as they kind of serve as mini little ball thingies. And they're also used in new methods of chemical synthesis, and we'll get more into that a bit later.
Can I pause for a moment?
Yeah.
The stuff that's on top of the slide you should know. For sure. Without writing, don't write it down. Just
Methyl
look at
ethyl.
it. We know methyl ethyl propyl and isopropyl. And didn't we build a T-butyl, which now is a tert butyl, which is the butyl in the T shape?
Yeah.
See, there's other ways to put 4 carbons together. What's the little squiggle lines? I'm asking the audience real fast, and then I'll turn it back over to Adam. No, the squiggle line means that it's attached. Oh, you're right. It's attached to something. Well, no, it doesn't have to be carbon. It just means that that is the ol, and the little squiggle line is whatever it's attached to. Thank you for.
Alright, so basically also, one last thing before we move on. You'll notice in these molecules, right? This boron has 5 bonds. Actually, no, it has 6. So just note that octet rules can be broken, and
Wow.
this goes beyond AP Chem, but basically if you guys choose to go over to AP Chem, this stuff transcends your formal charge stuff as well. So just keep that in mind. If you have like carbon with 6 bonds, boron with 5. So yeah, bonding is not a cookie cutter in AP Chem, or Chem in general. So just keep that in mind if you guys choose to like major in Chem college or something. It's kind of hard. Okay, so other superacids. So we have pentocyanocyclopentadiene. So that's the molecule on top, right? So I'll break this down since that's kind of a mouthful. So this acid, right? So normally you wouldn't expect it to form like these polymer chains, but basically this is kind of almost like a plastic acid, right? I say this in the sense that it forms these polymers, right, with itself, and you can see the acidic hydrogen of one of them is actually protonating the nitrile group of another one, and it forms these really long chains. And this is used in inorganic synthesis because they're weakly coordinating, so that's useful there. And then we also have zeolites, right? So these are just like silicon or aluminum oxides that are just like bound together in structures that form interesting shapes. And basically, if you treat these with anhydrous acids, you can actually form really strong acid sites within these like complexes. So you can see right there, between the silicon and aluminum, you have strong bronzite acid and strong Lewis acid sites. Alright, so somewhat theoretical ones. I say somewhat because this has been synthesized before. Basically, you have helium hydride. So yes, helium can bond to things. In case you didn't know, this was first synthesized at Berkeley in 1925. This is the strongest acid ever and will protonate any other element or compound. It has a theoretical pKa of -63, and I'll go into that a bit later. And this is often found in space, right? So, have you guys done spectrums yet?
Nope.
I'm on one.
Well, basically, right, light consistent with the spectrum provided from this molecule has been found in space, so it's like a spatial element, I guess. And additionally, more heliums can actually bind to this molecule in order to form larger helium-hydrogen complexes. So you can have things like He2H+, He3H+, all the way up to He6H+. Keep that in mind. So about the theoretical pKa of -63. So you guys probably take math classes. You're probably wondering, yeah, that's a pretty okay number to work with, right? That's a decent assumption, but you'd be wrong. So basically, pKa is a logarithmic scale. Basically goes up by a factor of 10 each time. So here's where the Hammett acidity function comes in, right? So if you have a pKa of -63, and you take, let's say, HCl, for example, which has a pKa around 0, you'll notice that this is actually 10 to the 63 times stronger than HCl. So it really makes, so it really just messes up your numbers, which is why you need a new way of like doing stuff with these, yes?
Why is it theoretical if it's synthesized?
Theoretical because of the fact that no one has really synthesized enough of it in order to actually do experiments with it. That's why. But the theoretical is probably pretty close to the actual, since math explains things pretty well.
Oh, there's more.
Okay, so then we have a superacid usage. So this is more of like what you actually use them for. A reaction catalyst. So you guys did the making an estimate. Did you guys do that?
Not yet.
Not yet. Okay. When you guys do that, you guys will use a strong acid, sulfuric acid, and basically these acids, since they're so strong, they're used to basically drop the activation energy required for a reaction, since they help the reactants just like interact easier. Then you also have alkylation reactions. This is just moving around alkyl groups, so like CH3, CH2, stuff like that.
They know those are methyl ethyl.
Yeah.
Me. Sorry, methyl ethyl.
PB.
Oh, methyl ethyl.
Alright, they're also useful in like protonating pretty much anything you want. So in oil cracking, for example, when you're breaking down hydrocarbons into more useful states, you'll use strong acid, and it goes back into petrochem. And then also the stabilization of organic compounds. We'll get to this later. But basically, certain molecules only are really stable if you add a superacid to it. If not, they just kind of break down, and you don't really have the molecule to work with. So that's just a diagram of carbon cations. We'll get to that a bit later. But basically, it's just a molecule in which carbon has a positive charge. Okay, so we have key superacid reactions. So we're gonna play like a guessing game, I guess. So let's say we take superacid, so pyrosulfuric acid, and let's say we react it with some sulfuric acid. So we'll just, I'll just take like hands now. What do you guys think will happen? Any random guess? I
The
don't-
chain will get big.
It'll make salt and then water.
It's actually true.
It could. That is one possibility. All right. Any other conjectures?
Sodium.
No? Oh yes.
It'll make a super stronger acid.
Oh yeah, that's a pretty good guess as well. So when you have two acids that react, sometimes you get a super strong acid, but other times you can get this. So as you can see right here, the sulfuric acid becomes a base. Yes, that is possible. So basically, if you have two acids reacting, right, and you have one acid that's like 10 to 20 times stronger than the other, that acid will basically overpower the other acid, and it'll basically protonate that acid. So as you can see right here, pyrosulfuric acid protonates sulfuric acid, and so sulfuric acid by definition is the base in this reaction.
Yeah.
So don't let like strong or weak acid labels define what you put as an acid in a reaction. So yeah. Alright, then we have something else. So we
Woo!
got magic acid. So this is what Braden mentioned. This is basically a combination of two strong acids. And let's say we
Magic
have
acid.
that. What do you guys think will happen?
That's nothing.
Oh.
Any conjecture? as to what
CH4.
will possibly happen?
Magic acid.
The recording. What'd you say?
No? Okay. So anyway, if you react an acid,
What?
a really strong acid with a hydrocarbon, it ends up protonating the hydrocarbon. So you can see right there we have a CH5 plus. You guys can take photos if you want.
Nathaniel.
Could you not?
So it takes the H.
Did you hear him? Donnie, y'all say hi.
You pronated magic acid.
You want me to send this to you?
Yeah, please.
Yeah, you guys can take photos.
You have my number, right?
Yeah. I
So
will.
this is pretty cool, as the magic acid is so strong that it basically forces the carbon to have 5 bonds. Don't write this on your test, by the way, unless Bender specifically asks what happens if methane and magic acid react. But yeah, that's just possible. So if we go more in depth, right, that's not actually making a pentavalent carbon atom. Instead, what it's doing, right, is you see the carbon and the H and the other H. You just look at this section right here. So those 3 molecules, basically the magic acid slaps a proton onto there, and it basically forces three atoms to basically share 2 electrons. So that's what's actually happening. So it's not methane having 5 bonds, it's methane having 3 normal bonds and 1 bond in which 2 electrons are shared between 3 atoms.
Whoa.
Kind of complicated.
Oh.
And you should have the labels there for acid-base stuff. Alright, so we have some more reactions in a video, which I'll show. So we have fullerene.
Buckyball.
For fullerene. You guys probably familiar with it?
You better be.
And then you have carburet acid. So about
What
this
the-
acid, it's a pretty good acid for organic synthesis, and this will explain kind of why. So in this case, it protonates the fullerene. So you get C60H+. So if you'll notice in a fullerene, carbon has 3 bonds, it just slaps an extra H+ onto it, giving it 4. And this is useful because this is the only acid known to actually protonate a fullerene without destroying it. Because other acids, they're so strong, or they're not gentle. Because this is like a strong but gentle acid in the sense that
That's
it,
so hot.
in the sense that it'll protonate them in a way that doesn't really destroy the molecules. As you can see here, this molecule
Exactly,
on,
exactly.
on your guys' right doesn't actually break down into like smaller parts because of the protonation. So that's useful for organic synthesis. Then we have other carbocations. So this is basically what I was talking about, right? So carbocation is anything in which C has a plus. So you can see right there, methanium, CH5 plus is on there.
Methanium.
You also have a C2H5 plus,
It's not Methanium.
which is on there as well,
Sorry.
and C3H5 plus. So if we look at these, you'll notice that that hydrogen over there appears to be having 2 bonds. So if you get into AP Chem, that's what we call a resonance structure, in which a molecule basically goes back and forth between various bonding states. And then we got a video on lab safety. So you're probably wondering what this does if you drop it in water. Well, now you're gonna see what happens.
Can you full screen that? Is that water being dropped? Or is it dropping on water?
We're dropping it on water. Yeah, so you can
Magic
see right here,
acid.
if you add a really strong acid to water, you're gonna get that. So then you're probably wondering, okay, if that yields that, then why don't we just pour the acid into the water, right? The acid's gonna be contained in the beaker, and you're just adding water, so it'll just splash in the beaker instead of outside, right?
Uh-oh.
Well, you don't do that because I accidentally. Well, you don't do that because if you actually do that, what ends up happening is.
Thank you both so much for helping me perform these dangerous experiments.
Yeah.
You should definitely check out both of their channels.
Yeah, so that's why you don't pour water into strong acids, right? So even though it's pretty bad, if you add the acid into water, it's infinitely worse if you add the
Yeah, it
water into
explodes.
acid. So that's just lab state. Thanks if you guys continue to go and pursue chemistry down the road. Yes?
What happened?
If you poured water and acid?
Yeah, like why did they do that?
So basically, you saw how when we poured the acid into water, it was really exothermic and it released a lot of heat, which is why it was like bubbling and like splashing all over the place. Well, basically, this water is going to splash into the acid, and it's going to basically go to the bottom, and then it's going to vaporize really fast and push everything out. Did you guys go over like grease fires?
Yes.
Yeah. So basically, it's a similar reaction.
what?
In the sense that
Grease
the water
fires with the
sinks
water.
into
Oh,
the acid,
grease fire.
reacts, produces a bunch of heat, and everything just explodes out. Yeah, that's pretty much it.
Wow.
Alright, I'll take any questions you guys might have. Yep.
So does the superacid like break apart the water? What does it do to the water?
So basically, actually, if an extra one, actually, easy. Okay, I'm gonna draw this reaction, right? So let's say these acids they yield H plus, yeah. We got H plus, and we got H2O, yeah. And basically, when this happens, this H plus gets slapped onto the H2O. So technically, you should write it as
H3?
H3O plus. This is basically a hydronium ion.
Whoa.
But we don't really do that because whenever you write that, it's just assumed that that forms. But basically, you just protonate water, kind of. That's what happens. And this process, depending on the strength of the acid, can be really exothermic. So if you put like delta H for like a really strong acid, it would be like negative, like big number, yes?
Wait, also I have another question.
Yep.
So you know how that one really strong acid was strong but gentle to the fullerene?
Yeah.
Why is it the only acid that can do that?
It's the only acid that does. So that's a very good question. I don't know. That is beyond my knowledge. Alright, another question? Alright, yep, that's pretty much it.
Alright. Stop it. been stopping in
Are you going
5
to the Monday night Sonoma lecture?
No, 5 seconds is a perfect
You'll be
time.
able to understand. Because this reminds me.